Welcome to my channel. This is my very first video and honestly I'm super excited to be doing this. Thanks for being here. In this video we are gonna talk about neural networks. They may sound complicated at first, but don't worry. We are gonna break everything down step by step so it actually makes sense. To keep things simple, I have split this into two parts. The first part is all about mathematics, like what's going on actually under the hood. And the second part is where we will jump into Python and write the whole thing from scratch. No libraries and no shortcuts. We will use just a simple plain code so you really understand what's happening. Also, I have broken each part of a video into smaller sections just to make it easier to follow. I'll be using my drawing pad here, so feel free to pause and sketch along if it helps. And if anything's confusing, that's totally normal because confusion is a part of a process and it shows that you are learning. Alright, let's get into it. So what is a neural network? At its core, a neural network is just a bunch of numbers and functions arranged in layers that work together to make any prediction. We call this structure a network because it's made up of different layers. An input layer, where your features go in, x1 and x2 in this case. There can be different kind of inputs such as height, age, pixel values, income, etc. There will be one or more hidden layers where most of the maths happen, and an output layer where the results come out, like a predicted number, any class, or a continuous value. Each layer has neurons. So here you can see in the hidden layer there are 3 neurons, and in an output layer there is a just single neuron. These neurons are like tiny calculators. They take in numbers, do some maths, and then pass numbers out. So what happens inside a neuron? Let me draw a single neuron here so you can understand what's really going on inside a neuron. Consider this as a single neuron. So here, as you can see, there are multiple neurons. I have just drawn a single neuron here. And imagine a neuron that takes two inputs, x1 and x2. These inputs gets multiplied by weights, w1 and w2, and then we add a bias term, usually written as p. Finally, the neuron applies a function to this sum. We call it an activation function and sends the result forward. The math looks like this. Z equals w1 multiplied by x1 plus w2 multiplied by x2 plus bias term b. Then this input, this output or z, the result gets as an input to an activation function, which gives us a predicted value. So let's pause here and define everything. Weights are numbers the network learns. They represent how important each input is. Bias is a little extra push added to the weighted sum. It helps the model shift the output, and an activation function adds non-linearity. We will talk more about this later in the video. If these things are a little confusing, don't worry. We will discuss everything again and again so that you completely understand the concept. I have given a real life analogy here. So we will quickly look at this analogy. Think of it like this. Imagine you are judging a smoothie. You test it, give it a score based on two things, sweetness and creaminess. Maybe sweetness has more influence than creaminess, so its weight is higher. And maybe your mood adds a slight positive bias. You combine those to decide, do I like this smoothie? Yes or no. That's just a neuron's job. It takes an input, multiplies the input with its weights, add a bias term, and after an activation function, it gives a predicted value as an output. Let's say we are trying to predict something using two measurements, maybe taking an input of income of a person in $K, $1,000, and second input maybe as a credit score, and the output will be 1 or 0, 1 representing if the company wants to give a loan to this person with this income and this credit score, yes or no. So we want to train our model based on these inputs. We will have 3 neurons in the hidden layer and 1 in the output layer. So the structure is input layer has 2 features, hidden layer has 3 neurons, output layer has only 1 neuron. Each of the 3 neurons is connected to both inputs. This one is connected with this one as well as this one. This second neuron is connected with this and this one. And finally, this third neuron is also connected with X1 and X2. That means each neuron in a hidden layer has 2 weights, W1 and W2, and a bias term. Altogether, the hidden layer has a weight matrix of shape 3, 2. So the shape of a W is 3, 2, and a bias vector of a shape 3, 1. Let me quickly introduce the maths dimension because this is very important to understand the dimensions of different matrices. We will take the input or the whole. So it's very important to learn the maths dimensions because there are 3 neurons in the next layer and each looks at the 2 inputs. The bias vector is 3, 1, 1 bias for each hidden neuron. So we calculate Z equals X multiplied by the transpose of a weight matrix plus the transpose of a bias term. We already know, you might be aware that from a linear algebra, that if we want to multiply the vector X and vector W, the number of columns of a X must match with the number of rows of a matrix W. So therefore we are performing transpose of a W here and multiplying it with the X, adding this term bias, it gives us an output Z. So the general formula is Z equals W1 X1 plus W2 X2 until Wn Xn plus B, whereas X1 and X2 and Xn are the number of features your data may have, and each input feature will be multiplied by weight, by certain weights, and added a bias term at the end. You now understand what a neuron does, what weights and biases are, what a layer is, and how data flows forward. Now we are going to run some real numbers through the network and walk through the math step by step so you can see exactly how a neural network makes predictions. Let's get started. So we will define an input matrix. So for now you understand we have an X matrix of a row 3, 2. So we have 3 number of examples and 2 features, and we defined weight matrix as the shape of a weight matrix is 3, 2 as well, but we will multiply the X matrix So we have 2 comma 3. We will multiply this with the W matrix and add a bias term. This is a general formula, and the formula and for each neuron here are some calculations. So what we will do, we will take the 2 comma 3 as an first example. 2 comma 3, multiply it by each weight, and this will give us an output. This will give us a Z as an output of each neuron. So 0.8 is the output from a neuron 1, 2.5 is an output from a neuron 2, and 0.4 as an output from neuron 3. Now we need to multiply or apply the activation function to this Z1. Let's call this as a Z1, as this is an output from all of the 3 neurons for an example 2 comma 3. Especially we use a ReLU activation function. It is very famous, and almost everyone uses a ReLU activation function inside the hidden layers. So ReLU stands for rectified linear unit, and it's defined as max 0 comma x. This means positive values stays the same and negative values become 0. So in order to apply a ReLU function on our Z1, what we'll do is we will see if there is any negative number, that will become the 0, and then positive numbers will stay the same. So sigma of Z, or ReLU or activation function of Z, equals this matrix, and we call this as an A1. So this becomes the activated output of a hidden layer for an example 2 comma 3. Remember, we just applied the complete maths on a single example 2 comma 3. As you can see here, we have 3 examples. We will repeat all of this maths. We will multiply 1 comma 5 with the weight matrix and apply and add the bias term. It will give us Z2, and then after applying activation function on Z2, we will get A12, right? And then similarly we will apply the same calculations on 4 comma 2. So we will multiply 4 comma 2 with the weight matrix, add a bias term, and then finally we will apply the ReLU activation function, and finally the A1, which is final A1, will be of a shape 3 comma 3, 1 row per sample and 1 column per neuron. Now you can consider this as an input to our second layer of output neuron. So as you can see here, just a quick revision here, we have an input with x1 and x2 features. We apply the we found the Z as well as applied the activation function, and finally we got a matrix, which is an output from this and this neuron. We do not have complete A1 here. I think I have shown it later in this video, but for now you can consider this 0, 2.5 and 0.4 as an output from 0 from this layer, from 0 from this neuron, 2.5 from this neuron, and 0.4 from this neuron. These 3 outputs from these neurons will be considered or taken as an input on this output neuron. So let me just quickly do maths here for other 2 examples. So we will repeat the forward prop or forward propagation. So this is 1 comma 5. Here you can see we had 3 examples, 2 3, 1 5 and 4 2. I'm just repeating it again. 1 5 multiplied by the same weight matrix, and it gives us the output as Z as this one, and then after activation function, like this one is a negative, so we put a 0 instead of here, and then for other two, these are two positive numbers, so we keep it same as it is. For third sample, we found out Z13 as this matrix and A13 as this matrix. And final, as I suggested above here, A1, the output, the shape of a A1 will be 3, 3. So here we have a final A1. This is the output from each neuron for each sample. So this is going to be output for sample 1, sample 2 and sample 3. Now we have an output layer. So here you can consider that we have completed calculating the outputs from 3 hidden neurons, and then the output from these hidden neurons will act as an input to an output neuron, right? So this will be considered as an input to the output layer for the sample 1. Then we will repeat again for the sample 2 and then sample 3. In our example, we have just a single output neuron and it connects with the 3 values from the hidden layer. So the weight W2 will be of a shape 1, 3. 1 being the single neuron, as we have single neuron, and it is connected with 3 input from the previous layer. So the shape of this W2 are the weight which is at the output neuron will be 1, 3. So W2, here you can see that this one is a weight matrix and this one is Z21, Z22 and Z23. These are 3 samples from here. These are, as I already told, these will be the input to the output layer. So this is an input. Here you can see the equation changed a little bit. Instead of writing X, I have written A, because this one will work as an input to output layer. This weight will be of a shape 1, 3 with 1 row and 3 columns. Since we are doing a transpose here, this is the transposed version of weight, and then we will add a bias term. So in our example, we have taken weight as this matrix and bias as minus 0.2. In the beginning, the weight W1 here, W1 and W2 are taken as a random small numbers, and bias terms are also random small numbers. With each iteration, these will be learned. So we will see ahead how these numbers are learned, but you can see that from the sample 1, sample 2 and sample 3, we got the Z as a weighted sum for our inputs, and then after adding the bias term, we get these 3 numbers. Then we will apply the sigmoid function. Remember, in the hidden layers we were using the ReLU activation function, but instead in an output layer we are using sigmoid function. So let me go through this one quickly here. In a ReLU activation function, if a number is negative, it is considered, or we get as an output 0, and then there is a linear function ahead. But in a sigmoid function, if a number is very high positive, it will give as an output 1 or near to the 1, and if it is very much very high negative number, that will give as an output 0, right? So in the output layer we are using the sigmoid activation function because we need number between 0 and 1. This will be considered as a prediction from an output layer. So we applied the sigmoid function on each of these numbers. So sigmoid of Z21 will be sigmoid of minus 2.21. I'm sorry, I just had to write a minus sign here, so while writing I forgot to put a negative sign here. Otherwise all other calculations are correct. So after multiplying this matrix with this one and adding the negative bias term, you will get this output, and then for the sample 2 you will get this result, and then for the sample 3 you will get negative 1.49. Finally, we will apply the sigmoid activation on this z2, and the formula of a sigmoid function is 1 over 1 plus e to power negative z. Sigmoid basically squashes any number into a value between 1 and 0, which is perfect for binary outputs. So if a number is very high, it will give, if a number is very high, it will give us an output near to the 1, and if it's a negative, the result will be a number that is very near to 0, and this sigmoid is perfect for binary outputs. Here is a formula. So let's calculate the sigmoid for each of these 3 numbers. So you can use calculator, and after calculations you will find out that the sigmoid of, or if you would put minus 2.21 here, the result will be 0.0989. So what this gives is, this final prediction for sample 1 tells us that it is 0.0989, but in our example there was an output y equals 1 for sample 1, and for sample 2 it was 0, and then for sample 3 it was 1. So just a quick intuition here. Let's say for an example, if a person is earning $2,000 or $2,000 per month and his credit score is 3, the company will give loan to this person. But if he's earning less, and even though he has high credit score, they are not going loan to this person. And if he is earning high $4,000 per month, but his credit score is not good enough, then but still I see that this company is giving loan to this person. So these are just a dummy example, dummy data that I took, and but the important thing is that for the example 1, if we have an output y true as 1, but in our example we got 0.09. So here is a final prediction matrix. We name it as y hat, which is equals the 3 predictions that our model made. So till now we have completed the forward propagation, which is core of a neural network and how it makes decisions. And now we will cover how to measure how wrong the prediction was using loss functions, and how to correct the network using backpropagation and gradient descent. So before going ahead, so I just wanted to give you the forward propagation flow again so you understand it completely. Here you can see we give an input, and then it gives us output as a z, which is the first calculation our neuron makes, and then it applies the sigmoid function and gives us an output a. This is an output from single neuron. Then this will be considered as an input to the second neuron, and then we define some different weights and adding the biases. This gives us z2, which is a different neuron. First calculation it will give us as z2, and then we will apply the activation function on this z2, and finally it will give us y hat, which will be the prediction from our model. So now we will go over loss function, which is measuring how wrong the prediction is, and then we will look at propagation or backpropagation, where we compute how to adjust the weights, and then finally the gradient descent. We will use the maths to improve our model. So why do we need a loss function. We made predictions y hat equals this one, and our true labels are our true numbers were 1, 0 and 1. Clearly, our predictions aren't perfect. We need a way to measure how wrong they are. That's where loss function comes in. For binary outputs like this in our example, we will use binary cross entropy loss as a loss calculation function, which is defined by this formula. And so for our example, the sample one y1 equals 1, we will put 1 here as an instead of yi, and for the y hat we will put 0.098, which is what our model predicted. So for sample 1 the loss is 2.314, for sample 2 this is the loss, and for sample 3 this is our loss. Then finally we take the average of our total loss, which will be adding all these terms and then dividing by 3, and it gives us the final total loss as 1.3542. This is the final loss after defining all these weights, biases and the predictions our model made, and then based on these and based on our y true labels, the loss is 1.3542. Now we will use the backpropagation, which is really the big idea. This is used to reduce the loss, and we use a method called backpropagation, and here's the quick tuition. So we will use the backpropagation to reduce this loss. Backpropagation, so we know the loss. So we will use the backpropagation now, and as you can see here, so we will use the backpropagation, which is used to reduce the loss. So now the big idea, how do we reduce this loss? We use a method called as backpropagation to reduce this loss, and here's the intuition. We know the loss, which is also sometimes defined by J as cost function, and the predicted value we do have y hat, and we had weight 1, weight 2, bias 1 and bias 2 matrices as well. Now we need to ask ourselves, how much did each weight contribute to this error? Then we adjust that weight, increase it or decrease it in the direction that reduces our error. We use this using a gradients, which we'll see later in the video. Think of them as a slopes. So here you can see if a slope is negative, we will increase the weight, and if a slope is positive, we will reduce the weight. How it is increased or reduced, we will see the exact formula later ahead. But for now, you can think of it as if the slope will be bigger, the more impact that weight had on a loss, right? And then we come across the forward propagation again, because this is very important. So in forward propagation, you saw that we calculated x. After defining x, we calculated z, and then z was used as an input to the activation function. We got a, then we did these calculations and we got z2, and after having activation function on this z2, we got an output. But what we do in backpropagation is we propagate backwards instead of going forward. So we need to see that a2 is defined by z2, whereas this z2 is defined by a2, but a2 is defined by z. So we need to see how much impact w1 W2, B1 and B2 have on our loss, which is what we calculate in backpropagation. The mathematics for this one is we use partial derivatives, which I thought to cover it in a second video, but for now you can consider backpropagation as our partial derivatives as where we calculate how much impact of weight 2 is on our loss function, right? Or how much loss changes with output. So if we calculate dl upon dy hat, this tells us how much loss changes with the output. If we calculate dy hat upon dz, this tells us how output changes with the weighted sum. So don't worry, in this video we won't go deep into every derivative, but you just should know that we in the backpropagation we try to calculate how much impact each weight is on our loss or on our final error. So if the weight 1 has high weight on our high impact on our error, our final j, which is our final l, which is the loss, then we try to decrease it. And if W2 do not have much impact on our loss, we may try to increase it a little bit. Otherwise we will decrease it using the gradients. But for now you can just take an intuition that we will use backpropagation to minimize our loss. We will use the gradient descent to minimize, but for the backpropagation we need to see how much impact W1, W2, B1 and B2 have on our loss. After finding the gradients, which is partial derivative or dl upon delta L upon delta W2 equals this thing, this matrix. Delta L upon delta B2 is this, and for the hidden layer we have delta L upon delta W1 and delta L upon delta B1. This is how much impact these weights and biases have on our loss. There is just one single last formula, which is theta new equals theta old minus alpha delta L upon delta beta. This is the final formula for gradient descent, and alpha is learning rate here, so it tells us how big a step we take in the direction of final or global minima. So here you can see that in the initial weights, after calculating the cost, it was the cost was very much high, and then after defining or calculating these gradients, we multiply the gradients by alpha and then subtract it from the old theta. This can be W or bias term B, and then again when we calculate the weights W1 and W2, which will be calculated again, and then finally when we take the loss, it will be reduced. So with each step the gradient tells us which direction to move, and the loss after each iteration is lowered. So we repeat this over and over again. We feed the data, right? We calculate the output, then we finally calculate the loss, and after using backpropagation and gradient descent, we update the weights. So for the weight, it will be W equals W minus alpha delta L over delta W. So this will the intuition behind this is we need to see how much impact does the weight have on our loss function. We will this can have a large impact, so it will be 2, 5, 6 or a higher number. We cannot simply subtract it from the weight matrix. If we subtract it like that, our updated weight may trigger like this. It will be it may never converge. It will go like this, right? So therefore we are multiplying by the learning rate, which is usually a small number, sometimes 0.01 or 0.1, and then after multiplying we subtract it from the old weights, and finally we get the new weights. So this is how the model learns. Every time we go through the whole process, forward pass. Every time what we do is we go with this flow. We have a forward pass, then we calculate the loss, then we use the back propagation, and then we use the gradient descent to update the weights and biases. This single loop or this single iteration is called iteration or epoch. When we do this many times with enough data, the model slowly learns. The weights settles into values that give us accurate predictions. So here you can see that after using the updated weights, the final so here I'm using the formula W1 minus alpha multiplied by delta L over delta W2, and it gives me this updated W2 weight matrix. Same for the B2, W1 and B1. So here you can see that this was just a single iteration, right? So now what we will do is we will use the W2, B2, W1 and B1, replace these in the place of these old weights. So now we will do is we will multiply 2, 3 with the updated weights and updated bias, and finally we will get a different Z1 value. After applying the ReLU function, we will have a different A1 matrix, and for the output layer we will have a different weight, right? And after calculations, after making all these calculations, we will get a different prediction matrix. Finally, when we calculate the loss, we will see that the loss will be a little smaller. Let's say in second round it may be 1.1, so the loss will be a little bit smaller than the previous one. And after repeating this many times with enough data, the model slowly learns. The weights settle into values that gives us accurate prediction without memorizing the data. And this is what makes neural networks so powerful. They learn from examples just like we humans do. So here you go. Finally, we looked at what a neural network is, how it processes data through layers, how it measures errors, which we called it as loss function, and then how is backpropagation, how does backpropagation works, and then how are the weights and biases updated. This is the foundation of deep learning. In the next video, we will take all this theory and implement it in Python. We will train a neural network on the same data we used here and even test it on my own handwritten digits. So if you enjoyed this and learned something new, please consider liking, subscribe and dropping a comment on my video. This is my very first video. I tried my best to help you guys understand the basic structure of a neural network and most importantly the maths behind it. So thank you so much for staying with me till here, and if anything is still unclear, let me know in the comments. I'll reply and help however I can. You have got this. See you in the next one. Thank you.